So I'd like to say konnichiwa, guten Abend, arigatou gozaimashita, und vielen Dank. It is a great pleasure to be able to come here at short notice to give you, or to be able to present some of our work, which I hope will be of some interest and maybe slightly different from some of the other things that you'll see. So, this work is about diamond in fibre. I'm going to introduce some of the concepts behind why people are excited about diamond and some of the interesting physics that underpins that. But quickly, what I want to get towards is something about how to use diamond, and particularly one kind of diamond, namely nanodiamonds. And some ideas that we have that we think are a bit different from what other people have been thinking of, that might give us some new opportunities. This work is a collaboration. Oh, that's a bit odd. That's a bit odd. There's more things on my other slide. This work is a collaboration between 3 universities. I'm, as Professor Brandt said, I'm at RMIT University. Most of the samples here were made at the University of Adelaide in the group of Tanya Munro. Much of the analysis, I'm pressing the wrong button, much of the characterization was done by my colleagues at the University of Melbourne, particularly Brant Gibson. And I'd like to acknowledge various sources of funding, mainly through the Australian Research Council, funding, and also funding directly from the various institutions. So, I'm introducing diamond. Of course, we all think we know what diamond is. This is not the kind of diamond that I really care about. Diamond has been going through something of a resurgence of interest at the moment for quantum applications, and there's been a huge amount of really beautiful work. Underpinning much of that work is the work that's been done in fabrication of devices and fabrication of substrates. And it's really, for me as someone in the field, I find it exciting that you can go to companies like Element 6 or Sumitomo and you can start to buy reproducible starting material. And this wasn't possible 10 years ago. Much of the earlier, beautiful breakthrough work was being done in natural samples, which might have beautiful properties that weren't replicated in other examples of diamond. Now we have some hope that we can go off to some fabricator, some company, and get not as reproducible as silicon, but some degree of reproducible starting material from where we can base our work. But as I said, this talk is not about single crystal work. This is about what is the cheapest form of diamond you can get, namely nanodiamonds. And these nanodiamonds have some rather interesting properties, which I want to talk about. And because nanodiamonds are relatively cheap, easy to incorporate or easy to manipulate, what we want to do is to see how well we can turn this kind of starting material into the sort of thing we could start to build a technology around. For many people, the interest in diamond begins and ends with this beast, the nitrogen vacancy color center. The nitrogen vacancy color center is a really remarkable defect in diamond. It's formed by a substitutional nitrogen being next to a vacancy, so a lack of a carbon atom. And nitrogen is a fairly common impurity in diamond. It incorporates well into the diamond lattice, and so it's relatively easy to make things. The nitrogen vacancy center is thermodynamically more stable than either a nitrogen or a vacancy alone. It comes in 2 forms that are routinely seen, the NV0 and the negatively charged NV-. I'm not going to worry about the NV0, it's the NV- that we care about for its particular electronic properties. And so here this shows the fluorescent spectrum that you expect when you excite an NV center in the green, such as with this laser pointer, you'll see an emission here at 633 nanometers, which is the zero photon line, and then this broad tail of emission. This rather busy slide here shows you something of the NV level structure. Again, it's only very recently that I think the NV center's level structure has been properly understood, and this is still rather surprising, given that the NV center is probably the most well-known color center in diamond. It's been known for at least 40 years, if not 50 years, but it's really only in the last year or so that this level structure has started to be understood. The structure, as far as we know, is unique amongst color centers in diamond and is one of only very few color centers in any solid state host that shows its properties. It has a triplet ground state here, and the transitions from the ground state to the excited state are approximately spin conserving. So you can excite up here to this excited with a green laser off resonance, you can excite to this manifold, and then you will see emission here in the red. The lifetime of this excited state varies from, depending upon the exact form of diamond you're in, but as a rule of thumb in single crystal diamond, it's about 12 nanoseconds. This emission here makes the NV center a bright single photon source, and if that's all it did, it would be quite interesting. But the magic, for want of a better term, that's gotten people really exciting is this side transition here, the singlet transition. And so every so often, if you are in the plus or minus one state, you can decay from this excited state manifold into the singlet pathway, emitting a photon in the near infrared, and then coming back to the spin zero ground state. Which means that in an ideal case, when you pump with a green laser here, you will optically pump your NV centers into this spin zero ground state. If you were in the plus minus one state, because you see this transition, the brightness from the spin plus minus one states is slightly less, so this gives you a direct optical readout of an individual electron spin, which you can then use to do individual nuclear spin readout as well. It's not perfect. I've described this as if it were a perfect spin conserving or spin non-conserving transitions. In fact, it isn't. There are finite branching ratios, and so the visibility of the fringes here is not ideal, but it's certainly enough to do single center spin readout. As I said, for many people, we begin and end with NV centers, but if you're interested in single photon work, there are now quite a few identified single photon emitters. Here is a list from a review that we wrote in 2011, and this is already out of date. So I hasten to add, though, although these centers here have all been identified as single photon emitters, none of them have shown the spin polarization and the room temperature quantum coherence properties that the NV center has shown. And it's not really clear that any of them will. Nonetheless, if you're interested in single photon generation, there are far more centers that are of interest, and in fact most of these have more desirable properties than the NV center in terms of much narrower line width, and if you could create these centers on demand, you might have some hope of actually building a single photon source in whatever range you want. The downside, again, is that there's only really 2, maybe 2.5 centers that can be made reproducibly. NV center is very easy to make. Silicon vacancy center is relatively easy to make. And these nickel silicon complexes, I'd say that's half a center. They have been remade in other groups, but it's not well known. It's early days yet, though. So there's a whole raft of different colour centres. There are a whole raft of different applications that you might want to put them to. And at the moment, what I want to talk about is not so much the application. I want to talk about how you interrogate them and how you get information about their local environment out. And so this slide here shows you a schematic of one of the standard experiments that people use in the field. You have a single photo, you have your sample here. This is where you've got your diamond single photon sources, your fluorescent nanodiamonds. You have a laser coming in here to pump. So this would be your green laser, and you collect your red laser out, your red light here that's being emitted, go through these filters, and you have two single photon counters that you use to do Hanbury-Brown twists interferometry to confirm that you have true single photons. And this is an example of the anti-bunching spectrum that you get from a typical, well, maybe not a typical, but this is certainly one of the results that we've got in our lab, where the coincidence or the probability that both of these detectors fire simultaneously goes to 0 when these path lengths are the same, indicating that the source here emits one and only one photon. Now, what I want you to take away from this is that whilst this setup works and is an ideal laboratory-based piece of equipment, this is not the kind of equipment that you would like to deploy in a scalable technology. These are very sensitive. Whilst it is possible to ruggedize them, they're not cheap to ruggedize, and they're certainly not small. And so what I want to talk about a bit later on is some of the ideas we have for trying to reduce some of this optics. I just wanted to quickly show, though, before I do that, an image of single center imaging. This is a fairly old picture now, again from our group. This is a substrate upon which nanodiamonds have been washed. This is the SEM image, and this, for the same area, is the fluorescence image. And you can see many bright dots here, and some of these bright dots would correspond to individual colour centres, and these regions here will be agglomerations of individual colour centres. So what we'd like to have is an approach that enables us to harness the power, harness the single photon emission from diamond colour centres. But what we would like to do is to take advantage of the great developments that go on in the field of photonics. Already? Oh my, sorry. Okay, I'll speed up. So this is some very old work that was done by Jim Robo, again when he was in Melbourne, of growing nanodiamonds on optical fibre end faces. And so here we have an optical fibre end face. It's been etched to show where the centre of the core is. And this is put into a CVD reactor, and this is a nanodiamond that's grown just by chance on the core. This way works, but there are issues with this. It's not very reproducible, and the coupling is not so great. Several groups have been looking at what we call pick and place. This is a great approach. It certainly works. It's possible to pick up individual fluorescent nanodiamonds that can be pre-characterized and moved to where you want them to be. So here, this is, again, this is from work done at University of Melbourne. A nanodiamond is being placed into the core of an optical fibre. It preserves its properties and can then be used for subsequent coupling to the nanodiamond. This is just for a bare optical fibre. This is some much nicer, more recent work from Oliver Benson's group, where a nanodiamond has been placed in the core of a wholly optical fibre. This is a wonderful approach. It's sort of the Rolls-Royce technique. This is a very hard approach to, it requires expert handling to move, you know, a 20 nanometer nanodiamond precisely to where you need it. And whilst it works, there are many failures along the way. One of the other approaches that's been talked about, and this again is from Oliver Benson's group, this is an approach I like very much, is dip coating, where they take a tapered optical fibre and they literally pass it through a droplet of, I think from memory, water, but the solvent's not so important, solvent containing nanodiamond, and they can put nanodiamonds on the outside of a tapered fibre. There are still issues here. They have evanescent coupling. There are mismatched materials, and it's one of the important things that this is not very robust. Nanodiamonds can come off. So we started looking at placing nanodiamond inside material. We're not the first people to think about this. Nanodiamond in PMMA has been looked at quite commonly. This is a set of slides from the Macquarie group, but the Stuttgart group was the first to start doing this. And people have looked at putting nanodiamond inside fibres, and these are actually fibres for textiles. And in fact, I was reading recently that you can buy suits where the wool has been embedded with nanodiamond. We didn't want to do that. We wanted to do optical fibres. And so we started our collaboration with the University of Adelaide, and their favourite soft glass is something called tellurite. So tellurite is tellurium dioxide here. You can make this glass at 900 degrees centigrade, and we can put the nanodiamonds in. So we make the glass here, but then the nanodiamond is incorporated at a slightly lower temperature. This is our first billet, and this is really quite an exciting result. I know it doesn't look like very much, but these swirls in here are nanodiamonds. And so the first sign, that was very good. The second sign, we started to get much better. These are some billets, and you can see that by changing the concentration of the diamond in the tellurite, we're improving the quality of the glass. This is a good time to point out one of the big problems with tellurite as a glass is that it requires an oxygen ambient. And this tends to burn the nanodiamonds, which means that you need to work fairly quickly, and you want to work at the lowest temperature you can get. Typically, nanodiamonds burn in oxygen at about 650 degrees. Again, we continued to refine. This is another example of 0.38 milligrams annealed of now pre-annealed nanodiamond in 30 grams of tellurite. Once you have this, you can leverage existing technologies, existing processes. This is a preformed optical fibre containing nanodiamonds. This is now an SEM of this, and this is our first attempt to build a microstructured optical fibre. This is done from a continuous piece of tellurite, so there are nanodiamonds all the way through this, and in fact this wasn't a very good sample. This sample here, though, I think really shows the proof of concept. This picture here is now a confocal image of the of the tellurite. Most of these bright spots here are in fact fluorescent nanodiamonds, which we can confirm by looking at the room temperature photoluminescence, and we can also observe very clear anti-bunching. So what this tells us is that we can put nanodiamond into tellurite, and we can extrude it into an optical fibre shape, and the nanodiamond properties are preserved. Not only are they preserved, they're actually better, and we believe some of this is due to the fact that the graphitic shells on our nanodiamonds are being burnt away. Graphite burns at around 400 versus the 670 degrees of the diamond, so we think we're getting some preferential etching and annealing. And we're also seeing that the NV minus to NV0 ratio is improving, which we put down to the fact that we're oxygen terminating the surface. And this has been seen in bulk samples. The concept is that ultimately we want to be able to take these nanodiamonds and put them inside the core mode of a single mode optical fibre with very narrow core, so that we get preferential emission into the fibre mode, and then we can use that as a fibre-coupled single photon source. And we've been looking also at other structures. We're looking further at microstructured optical fibres. And before Kohei gets up and gets really angry at me, I will conclude my talk there. Sorry, actually, Kohei should have been you, Professor Brunt. He's going to get me instead. So I'll just say, What we've done is we've been looking at trying to combine nanodiamonds with existing structures, existing photonic platforms. Telluride is by no means the only system that you could imagine for this, but we think that this is an interesting new avenue to pursue. So thank you very much.